The simplest approximation you can make for the exchange and correlation Hall is the local density approximation. But even though it's quite simple, it has been seen that it actually works in many systems. So why is that? So here we're going to describe the more important feature that makes LDA work in such different systems. And that's going to be based on the characteristics of the exchange Hall. So actually what we are going to do is we are going to compare the exchange Hall for neon atom, for the exact exchange Hall for the neon atom, and the one that calculated within the LDA approximation. And actually, as you know, this exchange Hall is actually related with the pair density. The pair density depends on two position vectors, r and r prime. So basically, this pair density is giving to you the joint probability of when one electron is located at position vector r, having another electron located at position vector r prime. So the electron located at position vector r is going to be like the reference electron, and this per density is giving to you the joint probability of having this electron here, having another one located at position vector r prime. So if in principle, if you consider like as a first approximation, if you consider that there is no interaction, no correlation between the electrons, you expect that that per density would be just the product of the two densities, the density at position vector r times the density at position vector r prime. But we know that this is just the first approach to that, because actually there is a correlation between the electrons. There is some correlation both related to the interaction between the electrons, which is called correlation, and because of the antisymmetry of the wave function, which is the exchange Hall. So here the effect of this correlation, both the exchange and the correlation here, are including the exchange Hall and the correlation Hall. And here we are going to analyze, we are going to make an analysis on the exchange Hall that we do know that satisfies very interesting some rules here. So the exchange Hall that we consider within the LDA approximation, where in the CONSAM method, where the electrons are considered like independent and with no interaction, is actually the exchange Hall for the uniform electron gas within the Hartree-Fock approximation. And it can be shown quite easily that this exchange Hall for the uniform electron gas within this approximation is given by this expression here. Okay, this expression here. And actually it has very interesting properties. Of course, within the LDA, the density that you have to plug here is the density located at the reference point. You have to substitute this n, which for the uniform electron gas is just a constant. Within the LDA approximation, you have to substitute this density with the density at point r. So let's analyze very briefly the characteristics of the exchange Hall of the uniform electron gas. As I've said before, it depends on two position vectors, r and r prime. As you can see here, that dependence is just on the modulus of r minus r prime, here on the modulus of these two distance between the two electrons here. So that means that with respect to the reference electrons on a sphere of distance r prime minus r, the exchange Hall on all this sphere here is going to be the same. So it has this spherical symmetry, which of course, it can be understood in the sense that the system we have is pretty simple. It's just a uniform electron gas. So because of this homogeneity of the systems, you expect to have that symmetry. So there is the symmetry associated to the uniformity of this electron gas. Besides that, you have that the maximum is located at the point where r prime is the same as r. So when r prime is located, when the second electron is located at the same point as the reference electron, r prime is going to be the same as r. Then you have that. That's going to be 0, and because of this denominator, you plot that figure here, that function here. You see that the maximum of the hole, or in this case it's negative, so the minimum of the hole is just located, because it's a hole, okay, it's negative, so the maximum hole, so the minimum value of the exchange hole is just located at when the second electron is located at the same point of the reference electron. So these are the main features that we can see here in the exchange hole for the uniform electron gas. By the way, here the function you have here is the Bessel function, the spherical Bessel function for the first kind. Okay, now we do know how the exchange hole for the uniform electron gas looks like. Now we're going to compare with the exact one, and actually we're going to do that for neon atom. Okay, and this is what Jones and Gunnarsson did in this reference here in 1989. So here they plotted the exchange hole for neon atom. The exact is the solid line here, and the LDA is the dust line here. So what's this plot here? So basically here what they consider is, in order to plot it, it depends on two position vectors, and making a plot on two position vectors, it's quite, of course, difficult. And so they consider the following case. So this is the neon atom, and the reference electron is just located at the position vector r. Once it's fixed, they consider the r prime, which is in the same direction as the direction of the position vector of the reference electron. So r prime is going to be parallel to r. So that this is going to be, in this case, it's going to be r prime minus r. That's going to be r prime minus r. So when in this case you have that r prime is smaller than r, you have that we are going to consider that value as negative. So we are getting closer to the nucleus in this case. And for that case where r prime, so the second electron is located farther than the reference electron, that will be just positive, and we are getting farther, in this case farther from the nucleus. So basically what they did here, they fixed the position of two r values. So the first one here, they fixed the r value to this value here. This is the Bohr radius. And the second figure here, they fix the position of the position vector or the reference electron to this value here. So in this case, it's closer to the nucleus. In this case, it's farther to the nucleus. And then they are plotting it as a function of r minus r prime, or r prime minus r. So here the 0 will correspond to that case where r prime is the same as r. And then the negative values, as I've said before, are those cases where r prime is smaller than r, so the second electron is getting closer to the nucleus. Okay, and the positive values are those that r primes are larger than r, so you are getting farther from the nucleus. Okay, we are going to see the features that can be described here and the differences between the exact and the LDA. Okay, the first thing you can see here is they are extremely different. They are very different, either in the value they have and in the shape that they have. They are very different for both cases, for position vector of the electrons getting close to the nucleus and those they are getting farther. Okay, they are very different. It's also interesting to see that within the LDA, when you are plugging the density corresponding to that position vector, the value you have for the exact and LDA, of course, considering that within the LDA you're able to get the exact density, the value for this exchange hole at r prime minus r equal to 0, so it means that r prime and r are the same, so it means that the second electron is located at the same position vector as the reference electron. You can see here that both are the same, okay, both are the same, but when you are going out from this position, you can see that it becomes very different. For example, you can see that closer to the nucleus, you can see that the exact exchange hole is getting bigger, and farther from the nucleus, it's getting smaller. So then you can see that the maximum of the exact exchange hole is getting closer to the nucleus, negative values here, and the maximum in the LDA approximation is just at r prime minus r equal to 0. So it means that r prime minus r here, we have maximum. You have maximum here, r prime minus r equal to 0. However, the maximum of the exact is when the second electron is getting closer to the nucleus. So there are many differences. So just in order to to make a brief summary of these differences, we can see that the LDA hole is spherically symmetric. That's important. That's what we have said before. With respect to a reference electron, you have all points where r prime minus are the same. So all the points that are distributed in this sphere are having the same exchange hole. However, that's not the case for the exact exchange hole. The LDA hole is spherically symmetric, while the exact hole has a more pronounced angular dependency. And secondly, you can see that in an atom, the exact hole is stretched towards the nucleus. You can see it's stretched towards the nucleus. The maximum is getting closer to the nucleus, whereas the LDA hole remains centered on its reference electrons, where r prime minus r is equal to 0. Here you have the maximum is located here. Okay, so it's clear, it's evident that the exact exchange hole and these LDA exchange hole are so different, and this is crucial in order to have the exchange energy. And exchange energy is an important contribution to the energy, a very important contribution to the energy. So being so different, why the LDA is working so well in so many systems? Okay, the key thing for that is the following. Actually, here we have the expression for the exchange and correlation energy, where of course it depends. Here you can write it in terms of the exchange and correlation hole here. Okay, if we do this change of variables, you can write r prime minus r equal to u, and you write this integral in terms of this new vector u. You can see we can get easily that expression here. Okay, as you can see here, the angular dependence on the u vector is just included in the expression of the exchange and correlation hole here. Okay, so when we are doing the integral with respect to the angular, the solid angle of the u vector, you just need to do this integral here on the exchange and correlation hole here, because here in the denominator it just depends on the modulus of u. So that's what we have done here. We are making the solid angle integration on the exchange hole, and the remaining integral on the u vector it's here. Here we are multiplying by 4 times p, and we are dividing here by 4 times p, just in order to have an average, because basically what we have here is a spherical average with respect to the angle of the u vector of the exchange and correlation hole. In order to be the average, you just divide on the value of the integral of the solid angle, which is 4 pi. So writing another way, we have that the exchange and correlation hole can be written in this way, where here you just have the average, the spherical average of the exchange and correlation hole. So what does it mean? It means that the exchange and correlation hole just depends the exchange and correlation energy that just depends on the exchange and correlation Hall through the spherical average. So we have seen that actually both the exact and the LDA exchange holes are very different. But what happens with the spherical averages of the exact exchange hole and the LDA exchange hole? And that's done in these two figures. Here we are having precisely the average, the spherical average with respect to these the angles of this u vector of the exchange hole, the exact one, which is again the solid line here, and the LDA, which is the dashed line here. For the same are position vectors as we have considered before, these and these ones, and as a function of the modulus of the u vector, which is basically the difference between r prime minus r. So as you can see here, that's very important. Even though the exchange holes, the difference between the exact and the LDA were so different, when doing the average of the two, they are getting very pretty similar. So why does the LDA work in so many systems? It works because the spherical average you are getting for the exchange hole within the LDA is pretty much similar to the exact one, as you can see here for this neon atom. And actually the exchange energy, which is an important key feature in order to have the total energy for the system, just depends on that spherical average. So it's we have a kind of cancellation with different parts so that the spherical average of the exchange hole we are getting within the LDA approximation is pretty much the same as the one you have for the exact one.